This is the second video in a two-part video series on section 6.4, Working with Taylor series, out of the OpenStax Calculus book, Volume 2. In the first video in this series, we discussed binomial series. In this second video, there is really not any new information to teach. It's simply a matter of using what you've learned in the first few sections of Chapter 6 and using binomial series in order to find other series using known series to solve differential equations and to evaluate limits. While we will not do a lot of solving of differential equations, since that is not the focus of a Calculus 2 class, I do want to expose you to this, as this is one of the major uses of calculus in later applications and in the real world. Let's take a look now at the first example. In example 1, we want to use a known series to find something else, find a different series. In this problem, we want to find the Maclaurin series for x sine of x, which is not a known series, by using the known power series for sine of x. Again, this series here was developed by using a Taylor polynomial, or in this case, a Maclaurin polynomial centered at a equals 0 and developing the formula. Now we want to take this known series for sine and use it to create a different series for x sine of x. To find an expression or a series representing x sine of x, we'll simply use the formula up here for sine of x. The only difference is x sine of x has an extra x at the beginning. So while this is a fairly simple problem, it does give us the power of using a power series. So again, we can simply write this as a monomial x factor multiplied by the series n equals 0 to infinity of -1 to the n, x to the 2n plus 1, divided by the quantity 2n plus 1 factorial. Now, because we have the x on the outside, we could pull the x on the inside. It does not depend on the limit or index of summation n, and that means it could come in or out at will. We'll pull it on the inside, and that will give us the sum from n equals 0 to infinity of -1 to the nth power, giving us that alternating behavior. The denominator will not change, but now the numerator instead will have an additional power of x, which is 2n plus 2. Now, if you want to think about the power that you now have on the x slightly differently, you could factor a 2 out of this and pull the 2 onto the x. While this is a perfectly acceptable format for writing the solution, there are others that would be just as acceptable. What I'm talking about by changing the format is that I could factor out the 2, since 2n plus 2 is equal to 2 times n plus 1. I could separate the powers, and it would also be acceptable to write this power series in this format. -1 to the nth power times x squared to the n plus 1, all divided by 2n plus 1 quantity factorial. Because the sine's power series is convergent for all real numbers, then we get for free that this power series is also convergent for all real numbers over the same interval of convergence. Let's take a look at another example. In our second example, we want to find the Maclaurin series for x squared e to the negative x using the known power series for e to the x. In the box below this problem, you will see the known power series for e to the x centered at 0. You'll notice from the condition at the far right that it is in fact convergent for all real numbers, which means we could plug any value we choose in for x and get an exact value for e to that power. For example, if I want to know what e squared is, I could replace x with 2 in this infinite polynomial, and it will generate exactly the value of e squared. For us, we wish to use that series to come up with a power series for an unknown series, x squared e to the negative x. In order to represent x squared e to the negative x, we need to think about what parts are similar to the known series and what are different. In this case, we have e to a power, but the power no longer matches the known series, which has a power of positive x. To make them match, we will simply take the x in the known formula and replace it with negative x. To complete this, we will then multiply by x squared. Yes, I know this seems too easy, and you're looking for the catch because it can't be that easy to do after you've struggled through the last 2 chapters, which are quite enormously difficult. You're really looking for the catch. But I'm telling you, there is no catch. That's it. That's all you have to do. Now, yes, you could separate the negative from the x in the factor negative x, the quantity raised to the nth power. That would give you the following: x squared times the sum from n equals 0 to infinity of negative 1 to the nth power times x to the nth power divided by n factorial. You could also bring the x squared that is currently outside the summation notation to the inside. Because it does not depend on the index, it can come in and out at will. However, this factor, x to the nth power, does depend on n, so it cannot leave the summation. If I combine the two together, since they have a common base of x, I would simply add the powers. This would then lead to the sum from n equals 0 to infinity of negative 1 to the nth power x to the n plus 2 power divided by n factorial. This represents a new power series based on the power series for e to the x. Again, because we use the power series for e to the x, whose interval of convergence is all real numbers, I get the same interval of convergence for the new power series, which represents x squared e to the negative x. Let's take a look at the third example. In the third example, I've stepped up the difficulty level just a tad, but still it's not going to be terribly difficult. We're looking for a new power series representation for the sign of the quantity pi times x, all divided by x cubed, using the known power series for sine of x. Again, the interval of convergence for the power series of sine x centered at 0 is all real numbers. That will tell us that when we find a power series for this unknown series, it will also be convergent over all real numbers. First, we compare what we're trying to find with the form of the known series. The known series is sine of x, where x is the argument. In the unknown series, our argument to the sine function is pi times x. The first thing we need to do is to replace the variable x in the formula for the known series with pi times x. That means that we can rewrite the formula now as the sum from n equals 0 to infinity of negative 1 to the n, open up empty parentheses to replace the variable x, and into the parentheses, we want to replace x with pi times x. That, however, is not the entire part. We also need to divide by 1 over, or divide by x cubed, but that is the same thing as multiplying by 1 over x cubed. Because the x cubed is independent of the index of summation, it can stay outside or come in at will. In this case, to combine it with the x that's on the inside, we need to separate the coefficient of pi from the pi times x inside the base being raised to the power 2n plus 1. That will enable us to write the sum from n equals 0 to infinity of -1 to the nth power times pi to the 2n plus 1 power times x to the 2n plus 1 power, all divided by, in parentheses, 2n plus 1, close parentheses, factorial, and pull in the times 1 over x cubed. You also have a choice to write 1 divided by x cubed as x raised to the -3 power. Now that you have these two with the simple base of x and it matches, you can use the power rule where when you're dividing and the bases are the same, you subtract the powers. That will let us write in the next line down that this becomes the sine of pi x divided by x cubed is equal to the sum of n equals 0 to infinity of -1 to the n pi to the 2n plus 1 times x to the 2n plus 1 minus 3 from the power rule divided by the quantity 2n plus 1 closed quantity factorial. Now we will simplify the 2n plus 1 minus 3, which of course gives us 2n minus 2. This is a perfectly acceptable way to leave this formula. It is logical, it makes sense, and it is easy to interpret and use. You could, however, if you wanted to, again factor the 2 off the power of 2n minus 2 and write it again as 2 times n minus 1. That would let you rewrite this in a slightly different format, but one which is equivalent to the original. This would be the same thing as rewriting that power as x squared to the n minus 1. And that is because one base with two powers has the two powers multiplied together, and 2 times n minus 1, the quantity, would give you 2n minus 2. That's all you need to do in order to use known series to rewrite and find formulas for unknown power series. Let's now take a look at a different example. In example 4, we are going to use a known series to find something else, but in a slightly different format. In this particular problem, we are to use the Maclaurin series, meaning centered at 0, for both sine and cosine to prove that the derivative of sine of x squared is 2x cosine of x squared by differentiating the known power series for sine of x. In order to differentiate this, we must first rewrite the sine of x squared in the format of sine of x. That means we'll take the first box, which gives us the known formula for sine of x, and use that to rewrite the formula for sine of x squared. That will give us the sum from n equals 0 to infinity of -1 to the n times x to the second power, replacing the x variable that was in the formula for sine of x, all raised to the 2n plus 1. Note that I replaced just the variable x in the formula for sine x with the x squared that is the argument for sine of x squared. Nothing else changes. When I do this, however, it will change what happens after that when I expand it. Since we want to differentiate it, we'll do this term by term. To differentiate it term by term, I will first need to rewrite the formula so that I can combine the x with the two powers into one power, and then I'll write out maybe 5 or 6 terms so that I can accomplish that. You might want to pause the video here, Do the work on your own and then turn the video back on to see if your answer matches mine. To simplify the formula, what I did was to distribute the 2 over the 2n plus 2. This gave me a power on x of 4n plus 2. Nothing else changed in the formula. The next thing I did was to expand it by writing out the first 5 terms. The first 5 terms are generated by n equals 0, n equal 1, n equal 2, n equal 3, and n equal 4. By replacing the index of summation n with the value that we're using each time, I will be able to compute and write out the first 5 terms of this power series. In the next line then, let's go ahead and simplify those and write them in a more recognizable form. This should give rise to the following. -1 to the 0 is of course 1. 4 times 0 is 0, plus 2 will give me x squared for the numerator. And the denominator, 2 times 0 is 0, plus 1 will give me 1, and 1 factorial is also 1. However, I am aware that if I reduce too much, I may lose some of the pattern that is developing. In that case, I'm going to go ahead and leave it as 1 factorial in case I need the factorial as part of my pattern. For the second term, the -1 raised to the first power will make the next term negative. 4 times 1 plus 2 leads to x to the 6th power. In the denominator, 2 times 1 plus 1 will lead to 3 factorial in the denominator. The following term has -1 squared, so it is beginning to alternate. The power on x will be 4 times 2 plus 2, which will give me x to the 10th. The denominator inside the factorial will give me 2 times 2 plus 1, which is 5 factorial. When I look at the fourth term, the -1 cubed will again make it negative, and from now on I'm pretty confident it's going to alternate in sign. The power on the x appears to be increasing by 4 each time. When I plug in 4 times 3 plus 2 more, I do get 14, which verifies that that is the pattern. As I look at the denominators, it appears that the denominators are increasing by 2 each time, starting with the odd number 1. When I multiply out 2 times 3 and add 1, I do get 7, which confirms that that is the pattern. That lets me predict ahead of time that the last term I've written out should be x to the 18th power divided by 9 factorial. Then I can actually put in the numbers and check to be sure that that is what I would get. This pattern continues forever, which is the reason for the ... Let's now think about what we need to do from this point. To recap, we're trying to find another representation for sine of x squared. Our goal is to use that to prove that the derivative of sine of x squared is 2x cosine of x squared using the power series representations. Now that I have a power series representation for sine of x squared, I'm going to find the derivative of it by differentiating term by term. Then I'll look for a formula to rewrite it as a power series. Let's do the differentiation term by term. Since this represents sine of x squared, I now need to take the derivative with respect to x of sine of x squared. This should give me the derivative with respect to x of the preceding power series that you'll find written above it. Let's move down to the next page so that we can get it all on one page together. Here are the 2 lines that were written directly above. Let's continue by taking the derivative term by term of the expansion of the power series for sine of x squared. This will lead us term by term to 2x, still over 1 factorial, since that's just a constant, minus 6x to the 5th over 3 factorial, the constant, plus 10x to the 9th divided by 5 factorial, minus 14x to the 13th over 7 factorial, plus x, oops, I forgot my constant, 18x to the 17th over 9 factorial, minus dot, 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 and it continues forever. At this point, we do have the derivative term by term for the power series expansion of sine of x squared. What we need to do now is to take that and prove that this is the expansion for 2x cosine of x squared. There are a couple of ways to approach this. You could continue to move by trying to get this to look like this power series expansion by finding a formula and manipulating it term by term. We'll take that approach first, but then I'll walk you through a different way of doing it that might be more simple for you when you're doing this at home by yourself. You will note here that the power series expansion for cosine does begin with a lower limit of summation of 0. So the formula we need to derive should be starting at 0 in order to make it match that pattern. That means that I need to look at this expansion that I have here and see if I can come up with a formula that will allow me to start with n equals 0. When I look at these, at first I'm not seeing a great deal of pattern in the numerators. I know that the powers are 5, 9, 13, and 17. However, we need to remember where they came from. They came from 2, 6, 10, 14, and 18, which are now the coefficients. In other words, one way to get that is simply to take a multiple of 4 and add 2 to it. So this means that I can take a multiple of 4 to get 6 by taking 4 times n and adding 2. Let's write this down first so that you can see that this pattern will work for the coefficients on the second, third, fourth, and fifth terms. Then we'll back it up to see if it will work, in fact, for the first term if we start with n equals 0. Again, when n is 1, the first value will be 4 times 1 plus 2, which will give me a 6. I'll need to fix an alternating behavior here as well, so I need a negative 1 to some power. Let's move over the 4n plus 2 so we have a little bit more room. For 10, if n is 2, 4 times 2 would give me 8, plus 2 would give me the 10. This seems to generate the numerator powers. Will it work for the first one if I start with n equals 0? 4 times 0 is 0, and 0 plus 2 is 2. It looks like 4n plus 2 is the correct coefficient to generate what we have here. To get the signs correct, it needs to start positive and then go negative. That means that I need to raise my power to the nth power. Since the 0th power applied to a negative 1 is positive 1, this will start with a positive and then alternate after that. What about the powers on the variable x? They're 1 less than the coefficient powers. Well, then I can just take 4n plus 2 and subtract 1, which would give me 4n plus 1. Now, what about the denominators? When I'm looking at the denominators, they're clearly all odd numbers in the factorials. To get an odd number, I have to double and then either add 1 or subtract 1. If I'm starting with n equals 0 and I want the very first one to be 1, would I need to subtract 1 or add 1? let's think about what would happen. If I take a 2n and I multiply by 0, I'll get 0. But the first denominator does need to be a positive 1 factorial, so I need to add 1. If you check, this will generate all the denominators that you have. This means that we have found a formula that will express the sine of x squared's derivative in terms of a new power series. Remember that this is, in fact, the derivative of the power series expansion for sine of x squared. How can we now prove that this is actually 2x times the cosine of x? This is where the other power series formula comes into play. Let's take a look at the known power series for cosine. The known power series for cosine is here underneath the known power series for sine. We're going to copy it and paste it down below so we can refer to it while we're working on this problem. What we need to do now is to figure out a way to get the formula that we have representing the derivative of the sine of quantity x squared to more represent the format of cosine. It looks like it's already fairly close. The only thing I need to do is a slight adjustment. One of the things I will want to do is to remember what it is I'm trying to prove. If you refer back to the original problem, you'll see that we're trying to prove that the derivative of sine of x squared is 2x cosine of x squared. Let's write that below so that we can also refer to that as we continue to work. Since I have a formula which shows that I have an x on the outside of that formula here, it does seem logical that we should pull one of these x's away from x raised to the power 4 times n plus 1 and pull it to the outside of the summation. Let's go ahead and do that step next. This derivative then would be equal to x by itself times the sum, n equals 0 to infinity, negative 1 to the n, times quantity 4n plus 2, times the quantity x to the 4n power, all divided by 2n plus 1, the quantity factorial. Now I was able to take the x to the first power out of the summation symbol because it does not depend on the index of summation n. That leaves 1 less to be on the power of x, so 4n plus 1 minus 1 leaves the power at 4n. This does look a bit closer to the formula we see here for the cosine of x. However, it has x to the 2n. We know that the argument to the trig function was not x, but x squared. So my next step is to rewrite x to the 4n as x squared raised to the 2n power. If I can get the cooperation of the scroll bar, which will give me x times the sum from n equals 0 to infinity of negative 1 to the n, or n plus 2, times x squared, the quantity to the 2n power. Realize that when you have one base and two powers, the power rule tells you to multiply the powers. So x squared, quantity raised to the 2n power, is the same as x to the 4n. That part at least now matches the formula for the known power series of cosine of x with the x replaced with x squared. However, we can see that we do not have the same thing in the denominator. In the denominator, it should be 2n plus 2n factorial, but I have 2n plus 1 factorial. The next step is just a bit of tricky algebra, as you might expect, which is basically to rewrite the 2n plus 1 quantity factorial as 2n plus 1 times 2n in parentheses factorial. That does give me the 2n factorial I need, but it also gives me an unneeded and unwanted binomial factor of 2n plus 1 in the denominator. It must be able to go away, which means look to the numerator. I haven't dealt with the 4n plus 2, but clearly I could factor a common 2 out of that binomial and write it as constant 2 times the binomial factor 2n plus 1. That gives me a common 2n plus 1 binomial factor, which will now cancel. Because the 2 is a constant, the 2 in fact can be pulled outside the summation because it does not depend upon the index of summation n. That will let me write this as 2x times the sum from n equals 0 to infinity of -1 to the nth power times x squared raised to the 2n power divided by 2n in parentheses quantity factorial. That is precisely the formula we would have gotten had we substituted x squared into the known power series for cosine and multiplied it by a 2x, which means we have proved that in fact the power series representation for sine of x squared differentiated term by term and converted into another power series does give us term by term the same power series as the function 2x cosine of x squared. Let's take a look at a different kind of example. In example 5, we want to solve a differential equation using a power series. This is in fact what's called an initial value problem because I do know something about the original function, which we have written as y of x. You could also have written it as f of x, but in this case, and often in differential equations, we use y of x instead since we typically deal with x and y, and adding f into the mix just makes it more complicated. We know from the beginning that when the x value is 0, the y value should be 5. This is the initial value that will enable us to determine exactly what function we need for y. A differential equation is one where you don't know what the function is to start with. I don't know what y is. Y, of course, is replacing f of x, so what I'm telling you is I don't know the function f. Instead, what I know is that the derivative of this function, y, is equal to 2 times the same function. This is what's called a differential equation, where I know something about the derivative of the function in relation to the original function itself. The initial value makes the entire thing an initial value problem. To use a power series to solve this, we're going to first suppose that there is a solution. In other words, somewhere out there in the world, there is a formula for y that will solve this. I do have some y of x, which is a power series. Since it's a power series, I know that it can be written in the format looking like a geometric series. For convenience, we'll just center it at 0. The c sub n represent the coefficients of each term. I don't know what the coefficients are yet. That's why they have to remain c with a subscript of n. In this case, however, I can expand it and write out some of the terms. This would be, of course, c sub 0 plus c1x plus c2x squared plus c3x cubed, and so on. That would generate a power series. I don't know what the power series is, meaning I don't know what the coefficients are. However, I do know a relationship for the power series, and that is the differential equation that says that the derivative of the equation is equal to 2 times the original equation. I'm going to use that now and write that below. To find the derivative of y, I can take the derivative term by term of its power series representation. By taking the derivative term by term of the power series representation, I would end up with C1, since the derivative of the constant term C sub 0 would be 0. Then I would end up with 2C2, since the power rule would bring the power 2 to the front, plus 3C3, oops, I lost an x, 2C2x, plus 3C3x squared. And if I continued, the next would be plus 4C sub 4 x cubed, plus continuing on in that pattern. Now, I know from the relationship you see boxed in red that this derivative should be 2 times the original, which means that I can now write down an equation which relates the two sides. C1 plus 2C2x plus 3C3x squared plus 4C sub 4x cubed plus forever should be equal to the original y of x, which I wrote in a generic power series form as an unknown constant C0 plus unknown constant C1x, and so forth. Now I need to be able to solve for the unknown coefficients. We know because of the uniqueness of power series that if such a power series exists, it is the only one that will solve this problem. So for the next thing I need to do is I need to figure out then how to equate the two sides. If this generates a power series and this generates a power series, the uniqueness of power series tells me they must be the same thing if they are equal. And they are equal, and we know that from the differential equation given in red. That means that C1 must be equal to C sub 0. It also means that the coefficients of the x term must be equal, so that 2C2 must be equal to C1. This is similar to what we did with partial fractions when we equated the coefficients to find out how to break apart rational functions. Similarly, we must have the coefficients of the x squared terms also being equivalent. 3C3 must be equal to C2, and finally, of the ones I've written, 4C sub 4 should be equal to C3. We could continue going in this pattern, of course, forever. This pattern doesn't stop. However, we do know one piece of information that will let us pin down a starting place, and that is our initial condition. The initial condition is now at the top, ringed in orange. Y of 0 is equal to 5. We're looking for an initial value that will let us get a hold on where to start with the coefficients. In the original function y, which we wrote here as a power series, I know that when I replace x with 0, I should get 5. So we are going to rewrite this part here as the power series representation for y, but we're going to replace each occurrence of x with a 0. Now you know what's going to happen when you replace all of those x's with 0. When I replace each x with 0, these terms all, you got it, go to 0. You gotta love power series. They are incredibly, I hate to say it, but yes, they are very powerful. Every term except the first term is going to go to 0. But that tells me that I know the value now of C sub 0, the very first coefficient. Moving back up to where we had our coefficients, if I know that C sub 0 is in fact 5, then that should give me a relationship that will tell me what C1 is. If C1 is C0 and C0 is 5, then C1 is 5. But then if I know what C1 is, I can find C2. C2 must be 1/2 of C1. but that means C1 is 5, so this must be 1/2 of 5. But if I know C2, yeah, you got it. There's a pattern developing here. If I know C2, I should be able to find C3. C3 is going to be 1/3 of C2, but C2 is 1/2 of C1. That will give me a 1/2 times a 1/3 of C1. That's giving me a factorial in the denominator. That's 3 factorial, in fact. If I continue in this pattern, notice what develops when I solve for C4. I get 1/4 of C3, but by substitution, C3 is 1/2 times 1/3 of C1, so I get 1/2 times 1/3 times 1/4 of C1. In other words, I've developed a pattern that will let me predict what is happening. So now I can rewrite the value of y using these known coefficients. Let's write this now down at the bottom. Before I can complete that, note that I do need to still plug in the value of 5 for C1. This will give me 1/2 times 1/3 times 5, and C4 will be 1/2 times 1/3 times 1/4 of 5. That makes 5 a common factor. That means that when we write it down below, we could in fact factor out the 5 so that we can write y as a function of x with the 5 as a common factor. We know that the value of y of x should be c sub 0 plus c1x plus c2x squared plus c3x cubed, and so on. However, we now know what the values of each of those coefficients is. Since the first one is c sub 0, and c sub 0 turned out to be 5 that we found from above, then I can write the first term as a 1 since I factored the 5 out. The next term would be c1x, but because I have solved for c1, I know that c1 is the same. It's also going to be a 1, but it's multiplied by x to the first. There is a pattern in that each of these looks like it is a factorial. So we could write the factorial pattern here as 5 divided by 2 factorial. And this, of course, would be 5 divided by 3 factorial. And this one, 5 divided by 4 factorial. Working backwards then, the pattern for C1 must be 5 divided by 1 factorial. That will let us write it in a predictable pattern that we can use to write a power series. The next term should be C2x squared. We found the pattern for C2 here to be 5 divided by 2 factorial. The 5 is factored out, so we will get simply the x squared divided by 2 factorial. For the next term, you could also, of course, write it as a fraction out front. The next term then should be x cubed over 3 factorial, with the following term being x to the 4th over 4 factorial. And this pattern continues forever. Now we can take what we know about y of x and write a power series representation for it. In this case, the factor 5 is a constant and will not depend on anything. It can be brought completely outside the summation notation. On the inside, it looks like I am taking the variable x and raising it to the n power. To make it work for the first term, I need to start n at 0, and I'll go to infinity. There's no alternating sign, so I don't need a -1 raised to a power, but it does look as though the denominator should also be n factorial. Will this now work for the first term? If I take x and raise it to the 0th power, I get 1. When I take 0 factorial is also 1, so 1 divided by 1 does give me 1 as the first term. In this way, we can use power series to solve differential equations. Let's take a look at a different type of example. In the remaining two examples, we'll use known series to find limits that previously might have been difficult to evaluate. In the first one, we want to find the limit of the function x times the sine of 1 over x. When we're looking at this is one that is notoriously difficult to prove, but we can do it simply here using known power series. In this case, what do you think the method for doing this would be? Yep, you got it. We are going to replace the sine of 1 over x with its power series representation, multiply through by x, and imagine what would happen if we took the limit as x went to infinity. In order to use the known power series, however, we do need to have the same center. Unfortunately, this representation for sine is using the center a equals 0, and our limit is instead approaching the value of infinity. Infinity is a problem for two reasons. One, it does not match the center for the known representation for the power series of sine, so I can't use it. Two, infinity is not a number, so you can never use infinity to represent the center of a power series, at least not at the Calculus 2 level. We'll have to apply a trick to enable us to rewrite the center so that it is something we can compute. Since we have the known power series for sine centered at 0, we want to replace the x approaching infinity with some dummy variable called a parameter, which is instead going to approach 0. In that way, we can make the limit approach the same value that is the center of the series. Let me write down some of the relationships that we're going to use. The dummy variable called a parameter that we're going to use in this case is t. We'll use a lowercase letter t, and we will let x be equal to 1 divided by t. If x is equal to 1 divided by t, then that must mean that t is equal to 1 divided by x. They do have an inverse relationship. Since that's the case, what then could we say happens as x approaches infinity? If x goes to infinity, then t has to be approaching 1 divided by infinity. But you know that a constant divided by infinity in a limit must approach the value of 0. So we can replace x approaching infinity with t approaching 0. Now, in our case, since we had positive infinity, we are going to approach from the right. This will give us this value. Now we're going to take a look at it, and we're going to see how we can implement it into the series itself. Because we're going to rewrite it in terms of t instead of x, we will also need to rewrite it inside the sum end. In other words, we will not be able to rewrite it using x's. We have to switch to using t's. However, we already have the relationship we need. We know that t is 1 over x, so we can replace the 1 over x with t, and we can replace this x with 1 divided by t. Let's rewrite the limit in its t form with t as a parameter. We'll now have the limit as t is approaching 0 from the right of 1 divided by t times the sine of t. What would the next step be? Now you know previously that this is going to give you the 0 over 0 form, which of course you could use L'Hopital's rule. In our case, however, we want to show this using the power series form for sine. To use the power series form for sine, then, I need to replace the sine of t with its power series form. In that case, I can simply rewrite this and multiply it at the front by a 1 over t. Using that representation, I will get the limit as t approaches 0 from the right of 1 over t times, and I'll use big red brackets for the sign representation. That will give me the representation of each term in sign, and I'm going to expand it. The first term would be x, but I have replaced x with t. That is going to give me t minus t cubed over 3 factorial plus t to the 5th over 5 factorial minus t to the 7th over 7 factorial, and so on. This will give me this value of sine of t, and I've multiplied it by 1 over t. By multiplying by 1 over t, I can now distribute that inside the parentheses so that I have the limit as t approaches 0 from the right of the value of 1 minus t squared over 3 factorial plus t to the 4th over 5 factorial minus t to the 6th over 7 factorial. Since each time I distribute 1 divided by t, I reduce the power on t by 1. Now, the next step, of course, is to plug it in. Since I'm approaching the t value of 0, when I replace each t with 0, they all go away, and I end up with just 1, which you should have memorized from the beginning of this semester, is, of course, the value of that particular limit. This then leads to our final result that we do get the value of 1. Let's take a look at a more sophisticated example of using known series to find an unknown limit. In this particular one, we are looking at the limit of expression that is not rational in form because it has an exponential inside of it. It also has a negative 1/2 power, which can be thought of as 1 over the square root. The 8x squared is polynomial in behavior, but because of the presence of the square root and the exponential, it's not rational. We can use known power series, in this case, the known power series for e to the x, to simplify this limit and to evaluate it. I've saved this example for the end because it is the longest one and the most complicated. You'll also notice here that in the numerator, this 1 minus 2x raised to the negative 1/2 power can be thought of as a binomial series. Let's start by writing that as the binomial series and expanding our terms. In order to do that, remember the formula that we use for binomial series. The formula is as follows. 1 plus x raised to the p power, p for power, will give us the sum from k equals 0, or you could use n instead, to infinity of p choose k, that's that factorial formula we learned, times x raised to the kth power. I prefer to use p and k because the way the book is using the n is backwards to the way that it is normally used in combinations when you study probability and statistics. I find it too confusing, so I've just switched to p and k instead. Remember that your formula for p choosing k is the same as p times p minus 1 times p minus 2 multiplied by one value less successively until you reach the level of p minus k with 1 added back in, all divided by k factorial. Now we're going to expand this and see what we get. By definition, remember that when k is 0, that we define that to be 1. Let's expand now and write out what the coefficients there are going to be for the p choose k part. I will put these in purple so you can distinguish them from the rest of the work. Negative 1/2 choosing 0 by definition, which is the 3-bar equals, gives you 1. Let's take a look at the next one. -1/2 choosing 1, by definition, is going to start at -1/2, subtract 1, and stop at 1. That means the only factor you have is the original p. This will just give us then the original p in the numerator divided by the 1 factorial coming from the value of k. This leads to -1/2 for the coefficient. Let's take a look now at -1/2, 2. If I look at that, again, using the p minus k plus 1 evaluation for it, this means that basically what I'm going to do is I'm going to continue multiplying by 1 less than -1/2 until I reach the level of -1/2 minus 2 plus 1 back, which is, of course, -1/2 minus 1, which is a -3/2. That means I start with -1/2, subtract 1 to get -3/2, and stop. Divide this by 2 factorial. You'll also notice, of course, as we learned in the first video for this section, that the power, or rather the number written on the bottom, the 2, tells you exactly how many factors occur in the numerator and also corresponds to the factorial that you have in the denominator. Let's write out perhaps 1 or 2 more values. Using the last rule that we mentioned, this means that because I have 3 written for the k value in the bottom, that I should have 3 factors. It should start with -1/2, subtract 1 to get -3/2, subtract 1 from that to get -5/2, and then stop, because that is 3 factors. Let's write out one more just to be sure we have enough coefficients. The last one we'll write out will be the -1/2, 4, which will give me 4 factors in the numerator: -1/2, -3/2, -5/2, and -7/2. In the denominator, I must have a 4 factorial to match k. I won't bore you with the details, but I'll let you pause the video if you want to actually go now and compute what those numbers turn out to be. I prefer fraction form since it's more meaningful to me and more precise in the sense of understanding what it means. Take a moment now to pause the video, compute those values, then turn it back on to check your answer. After computing the values of each constant, I ring them in green so that you can find them easily. Notice that they do alternate in sign for the simple reason that our factors are negative. So when we have an odd number, it will be negative, but when we have an even number, it will be positive. Now we're ready to write the binomial representation for the first part of this limit, the 1 minus 2x raised to the -1/2 power. Let's remind ourselves what the formula is. The formula is we will take each coefficient in turn and multiply it by x to the kth power. This will let us expand the numerator and write it in terms of that binomial series. I've gone ahead and written the formula for the binomial series here so that we can refer to it as we write it out. Notice that we've already computed the coefficients, the p choose k. What we have not done, however, is replace the variable x with what we have in our particular binomial. This value, it will only be x if that's what's in the binomial. However, we have 1 minus 2x to the -1/2 power. That means that instead of x, we have something else. We have instead 1 minus 2x to the -1/2 power. We use the -1/2 for p to compute the p choose k, but we now need to write this part in the format of a binomial series. We do have the 1, but we don't have the plus. That's taken care of easily by simply writing it as plus a negative 2x raised to the negative 1/2 power. That means, however, that in the formula we must replace the x instead with negative 2x. Computing now the formula, we know our first constant is 1, and that's when k is 0, the index of summation, or for us, in the form I've written here, n, but really that should be k. This means that I can now write this as 1 times the quantity negative 2x raised to the 0th using the formula, but with negative 2x in place of the x from the formula. For the next term, we found that negative 1/2 choose 1 was a negative 1/2 coefficient. So our next term will be negative 1/2, and then we will have the negative 2x raised to the first power. The third one we found was 3/8. This is when k is 2. When k is 2, we'll have a plus 3/8 times negative 2x raised to the second power. The fourth was negative 5/16, or rather, that's when k is 3. It's our fourth term. So negative 5/16, replace x with negative 2x to the third. We did do one more term. We found that when k was 4, the coefficient for the fifth term should be a positive 35 over 128. Replace the x with negative 2x and raise it to the fourth. We don't know what it will be after that because we didn't expand it any further. However, that should be enough for us to see what develops when we plug this into the limit. I now want to evaluate the limit. And in order to do that, I'm going to replace the binomial part with the series that I found for it, the expansion, above. This will give me the limit as x approaches 0 of those terms added together, which would give me a 1, and then I would have to multiply it out a little bit. Let's see, a negative times a negative would give me a positive, 1/2 of 2 would give me plus x. For the next term, when I square the negative 2x, I would get, well, what would I get? I'd get 4x squared, and then when I multiply by 3/8, the 4 and the 8 would cancel, and I would get 3/2 x squared. For the next term, if you want to work it out, you will need to cube the negative 2x, which will give us a negative 8x cubed. But the negative 8 and the negative 5/16, the negatives will cancel, and the 8 over 16 gives me a 1/2. So I end up with 5/2 x cubed. For the next term, negative 2x quantity raised to the fourth power would give me a 16x to the fourth, so it's also positive. And if you work that out, while you might have thought you had a pattern developing, the next term will kill your joy because the next term turns out to be, unfortunately, 35 over 8x to the fourth. No, I'm very sorry, but that does not lead to a predictable pattern, although it was looking good for a while there. This is only going to take care of the first part of the limit in the numerator. Now we need to deal with the minus x to the, or e to the x. The minus e to the x can be dealt with the known power series for e to the x. The known power series for e to the x is up here. It starts with 1 plus x squared over 2 factorial plus x cubed over 3 factorial. It is, in fact, x to the n, a normal geometric, divided by n factorial. Let's expand those terms below and continue the pattern. All of these will be inside parentheses with a minus in between. It starts with 1, and then we have x to the first over 1 factorial plus x to the second over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and so on. Again, remember that the expansion for e to the x centered at 0 does have the form of x to the n over n factorial. As we continue, the next part of the limit we need to take care of is the denominator, the 8x squared. Let's do that one in green so we can see the difference. I'm trying to use the colors to help you organize the different pieces of this limit. Since it's so complicated, you can't really write it in one line all the way across the page. As we look at this now, if I were to distribute the negative, would I have any simplification that might happen? Is there anything that might cancel? Anything that might combine together? When I look at it, I can see that the ones would cancel and the x's would also cancel. Let's rewrite just the numerator now in purple, divided by the denominator, but get rid of the negative with the brackets. I have, and I will write fewer terms, 1 plus x plus 3 halves x squared plus 5 halves x cubed plus 35/8 x to the fourth plus ... for the binomial series minus 1 minus x squared over 2 plus x cubed over 6. Oops, that should be a minus. I forgot to distribute my negative again. Minus x to the fourth over, gosh, what is 4 factorial? 24? Minus so on forever and ever. All of this divided by 8x squared. This is what is now inside of our limit. If I can squeeze the limit at the front, I will try to do that. This is the limit as x goes to 0. Now let's take a moment and cancel out anything that is clearly exactly the same. I do have a constant of 1 at the front and a minus 1 in the middle. Those ones cancel and they're gone. I also have a plus x at the front and a minus x at the back. They're gone. Now notice that what's left in the numerator, every single term has an x in it. In fact, every term has at least one x in it. Let's take a moment now to reduce these by dividing each term in the numerator by our monomial denominator, 8x squared. In other words, let's rewrite what's left by doing the division. This will give me the limit as x approaches 0 of 3 halves divided by 8. And no, I'm not going to work that out just yet. But x squared divided by x squared would be 1. So I only get the constant. The next term is 5 halves x cubed divided by x squared, which will give me the 5 halves with an extra x on top, still divided by 8, plus the 35/8 divided by the 8 from the denominator, x to the fourth divided by x squared would leave x squared on top, plus continue the binomial terms. Now let's reduce what's left of the exponential terms. If I take a negative x squared over 2 and divide by 8x squared, I get the ratio of negative 1 over 2 divided by 8. The x squared divided by x squared is gone. For the next term, I have a minus 1 over 6, also over 8, but x cubed divided by x squared leaves an x in the numerator. The next term will give me a minus 1 over 24 over 8, but x to the fourth divided by x squared gives me x squared. Of course, the exponentials also continue forever, but all the remaining terms must have an x in the numerator. In fact, the only terms that don't have an x in the numerator are this term, which I'm now going to box in red, and this term boxed in red. Remember that we're trying to find the limit as x goes to 0. You could see what's coming. What happens to all these terms that still have an x in the numerator? They all go away, and we're left with two complex fractions. To evaluate the complex fractions, remember that dividing by 8 is the same as multiplying by the reciprocal, 1/8. That means that we can rewrite the limit in the following form so that we can finally get the answer. This is 3/2 times 1/8 minus 1/2 times 1/8. By doing the simplification, I get 3/16 minus 1/16, which is 2/16 or 1/8. Since the limit of a constant is a constant, the answer to this limit is 1/8. This is a way that we can use the known power series for different transcendental functions to come up with limits. Are there other ways? Yes, of course there are other ways. But this is an example of how we can take something very complicated and simplify it with expansions of infinite polynomials. There are some for which there is no known representation, and a power series is the only way to write it down. For example, if you're thinking about the integral of e to the negative x squared, there is no known antiderivative. If you're looking at this, it's not going to go. There's no way. It's a well-known function called the error function. We can, however, represent it with a power series. And if we can represent it with a power series, we can do all kinds of things with it. Limits, derivatives, integration, just about anything we want. The error function turns up in all kinds of economic, statistics, probability, and engineering situations. It is a common function. We just don't have a known antiderivative in terms of an elementary function. I hope that you have enjoyed this chapter and that you've learned something about the power and the purpose for power series. This is the end of this video.